Rewind Earth. Not 1,000 years, not 1,000,000, billions. And watch how many times the chain nearly breaks. A different asteroid, a slightly wider orbit, a moon that never formed, a magnetic field that collapsed 2 billion years too soon. Any one of those moments, just one, and there is no one here to ask what went wrong. We talk about life appearing in the universe as though it is a reasonable expectation. But what if we have been measuring the wrong thing entirely? What if the question is not whether life can begin, but whether a planet can survive long enough, stable enough, lucky enough to let intelligence finish? We have spent decades searching for habitable planets, and we have found them everywhere. Thousands of worlds sitting at the right distance from their stars, with water somewhere on their surfaces or buried beneath their ice. The count climbs every year. The galaxy looks generous. But there is a problem. Every time we search for a civilization, every signal we listen for, every megastructure we look for, every sign that intelligence had time to build something, we find nothing. A galaxy full of habitable planets should not be silent. Unless a habitable planet and an Earth are not the same thing at all. That is the question we have been avoiding, and it may be the most important one we ever ask. We have one sample. That is the entire foundation of everything we think we know about planetary life. One world, one history, one outcome. And from that single outcome, we built an entire science. We defined what a habitable zone means based on Earth's orbit. We defined what liquid water looks like based on Earth's chemistry. We defined what an atmosphere needs based on Earth's air. That is not science. That is one data point dressed up as a pattern. The error is not unique to us. It is a trap built into how minds work. When something is familiar, we mistake it for normal. When something happens once, in front of us, we assume it must happen often. But the universe does not care what feels normal. Consider what Earth actually is, stripped of the comfort of familiarity. It orbits a star that is unusually quiet. Most stars flare and scorch and pull their planets through radiation storms that can strip atmospheres bare within the first billion years. Earth's orbit is nearly circular. Most planets discovered so far live in ellipses that drag surface temperatures through extremes no biology could bridge. Earth has a magnetic field that is held for billions of years, maintained by a churning iron core that did not cool too fast, did not slow too soon. Earth has liquid water that did not freeze and did not boil, a balance maintained not just by distance, but by atmospheric chemistry that adjusted and held for an extraordinary length of time. And Earth has a geological engine, plate tectonics, the slow recycling of carbon from rock back into air, that has regulated the planet's temperature across billions of years, like a thermostat that almost never broke. Each of those things sounds reasonable when you list them one at a time. None of them feels impossible. But here is what we keep not saying out loud. Every single one of them had to hold, simultaneously, for billions of years, without any of them catastrophically failing. Not for a century, not for a geological epoch, for the entire duration it takes for a single-celled organism to become something that builds telescopes and asks where everyone else is. That is not a list of conditions. That is a chain. Start with the moon. It is too large. By every expectation for a planet of Earth's size, we should not have a moon like this one. Most models point to a single, violent event, a collision with something roughly the size of Mars, early in Earth's history, that tore material off and sent it into orbit where it gathered into what we see tonight. A specific collision, a specific angle, a specific outcome. That moon, because of its mass, because of how close it sits, exerts a gravitational pull on Earth's axis that keeps our tilt stable across long timescales. Without that stabilization, the tilt could wander. And a wandering tilt means a climate that does not hold, ice ages that do not end, equatorial regions that freeze, polar regions that burn, seasonal patterns so extreme that ecosystems cannot build across generations. A lottery ticket drawn at random 4.5 billion years ago determined whether Earth's axis would hold still long enough for complexity to arrive. Then there is Jupiter. For decades we called it Earth's guardian, the great mass that swept the outer solar system clean, pulling dangerous debris away from the inner planets. The reality is more complicated. Jupiter does not simply protect, it redirects, it amplifies. Some models suggest it reduces the rate of impacts on the inner solar system. Others suggest it can funnel material inward during certain orbital configurations. What has become harder to dispute? The presence of a gas giant in that specific location shaped the entire architecture of this solar system. The arrangement of debris, the composition of the asteroid belt, the history of what has struck Earth and when, and how often. And that architecture may be unusual. Of the planetary systems we have observed so far, hot Jupiters, gas giants that have migrated close to their stars, disrupting inner planets as they moved, appear to be a common outcome. Systems with a Jupiter-sized world parked quietly in the outer region, in a stable long-term orbit, with a small rocky world sitting undisturbed in the inner zone, those appear to be less common. Whether rare enough to matter significantly is still contested, but the question is now being taken seriously by people who were not asking it a decade ago. Then beneath Earth itself, something else held. Plate tectonics, the process where the crust breaks into slow-moving sections that sink and resurface, dragging carbon back down into the mantle and releasing heat over geological time, does not appear to operate on every rocky planet. Venus is roughly Earth's twin in size and mass. Venus does not have it. Mars likely lost it. These worlds, our closest neighbors, sit inside what we call the habitable zone. Neither of them produced intelligence. Plate tectonics on Earth has been running for billions of years, quietly regulating the carbon cycle, quietly keeping the temperature from drifting past the boundaries where life cannot hold. A lottery ticket drawn inside the planet, in the arrangement of heat flow and crustal thickness and mantle viscosity that decided whether the geological engine would keep running long enough for evolution to reach its strangest destination. 3 draws: the Moon, Jupiter, the tectonics beneath our feet, and each of them had to come up winning. Here is the reassuring interpretation. The one scientists took seriously for decades, the one that feels like relief. Planets are everywhere. The Kepler mission alone confirmed thousands of worlds, with estimates suggesting hundreds of billions of planets exist in the Milky Way alone. Habitable zones, those bands of orbit where liquid water is possible, appear around star after star after star. Water itself has been detected in interstellar clouds, in asteroid debris, on moons across the outer solar system. The ingredients appear to be ubiquitous. And if the ingredients are everywhere, the logic follows. Earth-like worlds must be everywhere. Life must be everywhere. And somewhere in that vast population of living worlds, intelligence must have emerged many times over. The silence is just a matter of distance, or timing, or signal strength. We have not found anyone because we have not looked long enough, or far enough, or with the right instruments. The galaxy is not empty, it is just waiting to be heard. That interpretation held for decades. It felt scientific, it felt honest, it felt like the humble position, refusing to make humanity special when the universe is this large. It also may be wrong, not because the planet count is wrong, not because the habitable zones are wrong, but because a habitable planet and an Earth may not be the same category of object at all. Habitable means one thing: the temperature range where liquid water is possible. That is the entire definition. It says nothing about whether the water stays. It says nothing about whether the atmosphere holds for billions of years rather than millions. It says nothing about whether the magnetic field survives long enough to matter. It says nothing about geological stability or tidal forces or the orbital architecture of the system surrounding the planet. We discovered a definition, called it habitable, and then forgot that we had defined it to be that small. The rare earth argument, developed seriously by scientists Peter Ward and Joe Brownlee, does not claim life is impossible elsewhere. It claims that the specific sequence of conditions that allowed complex life to persist on Earth for billions of years is not guaranteed by a habitable zone. Complex life, multicellular, persistent, neurologically sophisticated, requires not just a starting point, it requires that starting point to hold for an extraordinary duration without catastrophic interruption. The longer the chain of required conditions, the more the probabilities multiply against success. Each condition alone may not be rare. 2 conditions together become less common. 5 conditions together become significantly rare. 10 conditions that must all hold simultaneously across billions of years, and the math begins to look very different from the hopeful count of habitable worlds. The most grounded interpretation is this: we may have been counting the wrong thing. The number of planets in habitable zones tells us how many worlds received a starting position. It does not tell us how many of them ran the entire chain. Life appearing, even simple microbial life, may not be the hard step. Biologists who study the history of Earth's own evolution point to a different bottleneck: the emergence of the eukaryotic cell, the complex cell with a nucleus, which appears to have happened once in Earth's history from a single, unlikely merger between 2 types of microbe. Once, after billions of years of simple life filling the ocean. And from that one event, every complex organism on Earth, every plant, every animal, every thinking creature descends. If that event required specific conditions and occurred only once, even on a planet as generous as Earth, then the lottery is not drawn once when the planet forms. It is drawn again and again across billions of years, and every draw has to win. That is the chain, and most chains break. If this interpretation holds, and it is contested, and it is not settled, and serious scientists disagree, then the silence outside our atmosphere carries a different meaning than we assumed. We looked at the galaxy and expected it to be loud, filled with signals, with megastructures, with the accumulated noise of civilizations that had billions of years to build. And we heard almost nothing. The standard answer was, we are not looking correctly. The rare Earth answer is colder. Perhaps the silence is not a failure of our instruments. Perhaps it is an accurate measurement. Perhaps across the hundreds of billions of planets in this galaxy, the number of worlds where every link in the chain held, the right star, the right orbit, the right moon, the right magnetic field, the right geology, the right collision at the right angle 4 billion years ago, the right cellular merger at the right moment in the right ocean, is very small. Perhaps single digits, perhaps fewer. And if that is true, then the question of where everyone is dissolves. They were never there. The chain never completed. One link failed. Too early, too late, too cold, too chaotic, and the story ended before it could begin to speak. We did not win because we were special. We did not win because intelligence is the universe's plan. We won because the chain did not break. Billions of years of draws, and everyone came up just sufficient. Not perfect, not guaranteed, not inevitable, just sufficient to let the next draw happen. And here we are, the product of a streak of narrow wins so long and so improbable that it looks, from the inside, like it was always going to happen this way. It wasn't. The hardest thing about this idea The thing that makes it feel less like a scientific hypothesis and more like a verdict is what it implies about everyone else. Not that they failed, not that they were destroyed, simply that the chain ran for a while and then one quiet link gave way and the story stopped accumulating. No signal, no ruin, no warning, just silence. The same silence we are still listening through. Imagine a lottery ticket floating in the dark. No one bought it deliberately. No one knew what numbers to choose. It was printed by the slow physics of a collapsing gas cloud, punched with the right numbers by a moon that should not exist, and a planet that kept recycling its own skin for billions of years, and an ocean where one cell swallowed another and something irreversible happened. And it won. Not because someone chose it, not because it was the only ticket in play, but because of all the chains that ran. And most chains run for a while, and most chains break. This one held. We are the improbable end of a very long chain. The question is no longer whether other chains exist. The question is how many of them are still running.